Hi, welcome back to the channel. So in this video we are going to see implement frequency response of second order system. So we are going to write the code, Matlab code for implementing frequency response of second order system. So for this, here we will first consider what is the numerator value. So numerator value is 1 and the denominator value is, we'll consider something like 1, 1.414 and 1. So if I write num of 1 is equals to 1, the numerator value is 1 and denominator 1 is equals to means, so if it is 1, 1.4141 like this, these are the coefficients value. So here it is just like this. 1 is the numerator, corresponds to num1, and denominator is coefficient of, here it is 1, so coefficient of s square is 1 and coefficient of s is 1.414 and the constant is 1. So this is the h of s function. Okay, so next, the standard second order system is h of s is equals to omega n square divided by s square plus 2 zeta omega n s plus omega n square. So comparing here with this, omega n square is 1, so omega n is 1, 2 zeta omega n equals to 1.414. So zeta equals to 1.414 by 2 since omega n is 1. So zeta is equals to 0.707 or 1 by root 2. So zeta 1 by root 2 or 0.707 indicates that it is critically damped system. What is the meaning of this? Critically damped system returns to its equilibrium position in a short possible time without oscillating. So in critically damped system there is no oscillation and there is no overshoot. So it is attaining its equilibrium position in a shortest possible time. Okay, so that MATLAB code we'll see, and the frequency response of the second order system. So this is a second order system s square. Okay, so now MATLAB code, if we see this, first clear all, close all, and here we are defining the numerator and denominator. This I already told, defines the coefficient of numerator, coefficient of denominator, and omega is equals to 0 to pi. That this is a range, 0 to pi is a range, and the step size is 0.01. So this is the calculation of frequency response of the system defined by the numerator and the denominator at the frequency specified in the range omega. What is that? 0 to pi. So h equals to freq, freq s is, it is going to calculate the frequency response of the system for a range, the numerator and the denominator. Then you should do the magnitude of absolute value of h and the phase, the angle of this. So magnitude stands for, it is the absolute value of this, and phase stand for the angle. Okay, calculate the magnitude of complex frequency response h and calculate the phase angle of the complex frequency response h in radian. Then we should plot this. For this we'll use the figure. It is going to create the new figure window, subplot. It is going to create the subplot grid with 2 rows. So it is just like this. So it is first row, second row, column means 1, so 2 rows, column 1. Okay, and select the first subplot. First subplot means this one. So first picture is appearing here, that is called as 211. The second picture is appearing here, it is called as 212. 2 rows, 1 column, first diagram. 2 rows, 1 column, second diagram. That is the meaning. So first one, 211, with respect to 211 we should plot the omega and the magnitude, then x label frequency, y label magnitude. It's a frequency versus magnitude for case of the plot number 1. Entitled magnitude response system of h1 grid on. Next, similarly subplot 212, so same, copy and paste, everything is same for the second subplot. 212 and 211 is the difference. This will plot the magnitude and this will plot the phase. So how the magnitude plot will come like this, magnitude versus frequency. So it is frequency and magnitude, omega and magnitude. So here it is omega and phase, that is frequency versus phase. So it is like this. Okay, so this MATLAB code we are going to see here with the help of this MATLAB code. Okay, so we have already typed these values. Very important is this numerator and denominator values, and this range, frequency response of the system calculated by this, magnitude, phase, we should define it for a h. Then this is for the subplot number 1 and this is second. After this, just run this program. So after running, here the waveform appears like this. Okay, so you can just see this waveform. It is a magnitude plot spectrum of h1, magnitude versus frequency, and it phase spectrum, phase versus frequency. So magnitude is 0 to 1.5 here, and it is 0 to 3.5. So here magnitude value is decreasing. You can observe magnitude value is decreasing. Okay, and here the phase value is towards the pi value. That value is, we have written as, here it is a pi value is 3.142, so it is decreasing in radians, and the magnitude value is decreasing. Okay. So these are the plots for what type of system? Critically damped system. That is, zeta value is 0.707 and omega n is 1. Okay, so this is what I can observe, 0.5 and 1. So in between that 0.707, it is a zeta value damping factor. Okay, that's what you can observe from this frequency response of second order system, critically damped system. Thank you. We'll see in the next video like this. Similar type of videos you can watch on this channel. Stay tuned to this channel. Click on the bell icon for the latest notifications. Thank you.